Section 7.6 for Algebra 2, solve exponential and logarithmic equations. There's several different sections. I think there's 4. So I'm going to say, let's just equate the exponents. So here I have 7 to the 3x plus 4 equals 49 to the 2x plus 1. Well, I can leave this as is, and I can write 49 as 7 squared. And then what do we do to exponents when we raise an exponent? When we raise an exponent to an exponent, you multiply. So 7 to the 3x plus 4 equals 7 to the 4x plus 2. Don't forget to distribute that. And since these are the same base, these exponents must be equivalent. So 3x plus 4 must equal 4x plus 2. Subtract 3x from both sides, you get x. Subtract 2 from both sides, you get 2. X equals 2. And you should and could go back and verify that. 7 times 2 is 6. 6 plus 4 is 10, so that'd be 7 to the 10th. And on this side, you'd have 49 to the 5th. And certainly, 7 squared raised to the 5th would be 7 to the 10th. So that checks. 81 to the 3 minus x, 1/3 to the 5x minus 6. What base do these have in common? In this case, we only had to change one of the bases. I'm going to say these have base 3 in common, and 81 is 3 to the 4th. And that's raised to the 3 minus x. And in this case, that's 3 to the negative 1. And that's raised to the 5x minus 6. I'm going to take a little bit of a shortcut since I have the same base. This would be 12 minus 4x equals negative 5x plus 6. Add 5x to both sides. Subtract 12 from both sides. X equals negative 6. And I already did these, went back and checked them, and those are some pretty big numbers. It's 81 to the 9th, and then it's 1/3 to the negative 36, but they check out. Again, what base do these have in common? Oh, looks like I chose another 3, but I can write this as 3 cubed to the 4x minus 1 equals 3 squared to the 3x plus 8. Multiply exponents, and again, since they're the same base, their exponents must be equivalent. So 12x minus 3, don't forget to distribute, equals 6x plus 16. And I'm not going to then spend the time to solve that. You guys hopefully can isolate x. Actually, you'd get 6x equals 19. So x is just 19 over 6. And they likely leave it like that. If you want to change it to an exponent, you can. I mean a decimal. All right, so that's equating exponents. Here's where I think logs really come in handy. I want to undo an exponent. 2 to the what is 5? Well, in your brain, you know it's a little more than 2, but what is it? So if I log both sides, so I'm just going to log both sides, sort of like taking the square root of both sides. Remember now, the property of log says this x can come down front. This is the magic. And how do I get x by itself? Well, it's just being multiplied by log 2. So I'm going to divide by log 2. And since I used base 10, then my calculator can do the work. And I take out my calculator, and I type in the log of 5 divided by the log of 2. And I get 2.32. And we know that makes sense. X equals 2.32, because we know it's going to be a little more than 2. Now, incidentally, I could have taken the ln of both sides, and then x ln 2 equals ln 5, and divide both sides by ln 2. And if I did that, just to show you, I take the natural log of 5 and divide by the natural log of 2, and I get the same exact answer. So you can use ln or log. I think in the past I told you guys I like to use ln because I have to write less. Just a little bit of same idea, just a little different. Again, I'm going to, in this case, I'll use ln. ln of 7 to the 9x equals the natural log of 15 The 9x comes down. Divide both sides by ln 7. So 9x equals ln 15 divided by ln 7. And that's 1.39. And then I can divide both sides by 9, and whatever that turns out to be. And again, you can always plug it back in and check it. Really, you should. This should be a pretty small fraction, right? Because it should be something just a little more than 1. Because 7 to the first is 7. 7 squared is 49. So, yeah, actually it's a little more than 1. These 9s would cancel, and you get 1.39. What about this one? Order of operations, add 7 first. Then divide by 4. Now it's just natural to use take the natural log of both sides here, because ln e just undoes e. So you get negative 0.3x equals ln 5, and then you would just divide by negative 0.3. And x would equal whatever your calculator tells you that is. So here is an inverse operation. Take the natural log of an exponent whose base is e. Now, just to show you, well, Viv, what about that rule? Well, we can do the rule where it comes down front. Negative 0.3x natural log of e equals natural log of 5. Well, the natural log of e is just 1, because ln says, what do I need to raise e to get e? Well, that answer is 1. And just to prove it to you, I'll do the natural log of e to the first. And the answer is just 1. Sorry about all that parentheses. I don't like that operating system. So that's how those work. Make sure you follow order of operations, and when you're ready to undo the exponent, log or natural log both sides. And natural log totally undoes e. So certainly use that if you have e to the something. You could use the log, L-O-G, but it's a little more work, less efficient. All right, solve a log equation. Well, if I have ln of 7x minus 4 equals ln of 2x plus 11, then 7x minus 4 is just equal to 2x plus 11. And then subtract x from both sides, add 4 to both sides, divide by 5, and x equals 3. And you should check it, because 7 times 3 is 21. 21 minus 4 is 17. 2 times 3 is 6. 6 plus 11 is 17. That checks. Again, same base, so 4x minus 1 just equals x plus 5. 5x equals 6. X equals 6 over 5. A little harder to check, but if you have the same base, you can just equate the logs, just like when you had the same base, you could equate the exponents. Last section is, I forget what they say, exponentiate it or something. I say use the definition and the properties of logs. So what's the definition of log? 2 to the 5th equals x minus 6. 2 to the 5th equals x minus 6. That's using the definition. We know that's 32. Add 6 to both sides, and x equals 38. And if I put 38 in there, I'd get 32, and certainly 2 to the 5th is 32. That checks. Here I'm not ready to say 5 squared equals 12x yet, because I have this 1/3. So multiply both sides by 3, and log base 5 of 12x equals 6. Now I can write 5 to the 6 equals 12x. Divide both sides by 12, and x is whatever 5 to the 6th over 12 is. That's a big number. Now we're going to use properties of log and the definition. So remember, I have a sum of two logs. So what did that look like before? That was a product. I'm going to put the x first. So all I did was, remember, condense this. And then I have log 4. Actually, I'll use a definition right now. 4 cubed equals x times x plus 12. So what do I have? A quadratic. 4 cubed is 64. Factor, I believe 16 and 4 works, plus 16 minus 4. Now notice, what would my two x values be? Negative 16 or positive 4. Now if I put a negative 16 up here, I'd get log base 4 of negative 4, when we know we can't raise 4 to anything and get a negative. So this answer can't work. 4 must be the only answer. Even if you put negative 16 in here, we can't, there's nothing I can raise 4 to and get a negative 16. So negative 16 just doesn't work. We should check 4. 4 plus 2 is 16. We know 4 squared is 16, so that would be 2. If this is 4, 4 to the 1 is 4, so 2 plus 1 is 3. That checks. Let's do it one more time. Again, this was if I condense this, it's a product. This is base 10. So 10 squared equals 5x times x minus 1. I'm going to distribute this, 5x squared minus 5x, and I'm going to subtract that 100 from both sides. I'm going to factor out a 5. And then I'm going to factor the trinomial, x minus 5, x plus 4. So x equals 5 and x equals negative 4. And again, if I go all the way back to here and I plug negative 4 in, I'm going to get answers of negative. And there isn't anything I can raise 10 to and get a negative answer. So this doesn't work. There you go. Solving exponential and logarithmic equations.